Welcome to the viewers. Now today we discuss Hermite Hermite's polynomial. At first we are going to define this. Now Hermite polynomial of degree n is defined by h and z is equal to sum of k is equal to 0 to n by 2 box of 0 to n by 2 minus 1 whole to the power k n factorial by k factorial n minus 2k factorial 2z whole to the power n minus 2k, taking it equation number 1. Box of n by 2, that is n by 2 if n is even and is equal to n minus 1 by 2 if n is odd. So it is our definition criteria. Simply Hermite's polynomial of degree n given by this, and where we consider as n by 2 is equal to n by 2 if n is even. That is, box definition of the box here is different. It is not the greatest positive integer, but we use two different branches in this manner by notation. N by 2 n is even and n minus 1 by 2 if n is odd. Now we create generating function for Hermite polynomial. Now if we study it for the generating function, Hermite polynomial is obtained from the coefficient of t to the power n by n factorial on the expansion of exponential of 2tz minus t square. That means if we consider, so let us consider the expansion exponential of, that is e to the power 2tz minus t square. We find the coefficient of t to the power n by n factorial on this expansion. Now e to the power 2tz minus t square, that will be equals to, if we break this, 1 plus 2tz by 2z square t square by 2 factorial dot 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 up to 2z to the power. Now here we consider the cases of the polynomial, because we are taking the coefficient of, from the definition of polynomial, is 2z whole to the power n minus 2k. That's why we only take 2z whole to the power n minus 2k into t to the power n minus 2k by n minus 2k factorial plus dot dot dot. and multiply with e to the power minus t square, that is 1 plus minus t square minus t square by it is 1 factorial plus minus t square whole square by 2 factorial in this way plus minus t square whole to the power k by k factorial. And now in the following expressions, that means if we multiply it minus 1 whole to the power k into this, that means twice k adjust, so t to the power n coefficient by it is k factorial by n minus 2k factorial. So if we take the coefficient, that means in the expansion, so that the coefficient of t to the power n in this expansion is, and if we take it here, that means there are the two different symbols here. For n is even and odd, there may be two possibilities. So sum of k is equal to 0 to n by 2 box of, and if we multiply it minus 1 whole to the power k and t to the power 2k into t to the power n minus 2k, that is t to the power n coefficient. And here we can calculate 2z whole to the power n minus 2k. Here it will be k factorial into n minus 2k factorial. And obviously this idea that takes the definitions of Hermite polynomial already we get. Hence we can say h and z equals to sum of k is equal to 0 to up to infinity. If we take an infinite way, minus 1 whole to the power k n factorial by 2z whole to the power n minus 2k by k factorial into n minus 2k factorial. If we take as wider definitions, because in the earlier stages we here taking this form of in a finite level and this infinite integer, because we don't know how n goes from, either it may be odd integer or it may be even integer. That depends on some of the conception about this. And k takes from 0 to infinity, that's why, because we don't know here the nature of n may be infinite terms. And we can write e to the power 2tz minus t square, that will be sum of n is equal to 0 to infinity, k takes from going to n, and it is the coefficient of t to the power n. We taking adjustment here for n factorial, but we are taking the shortage of n factorial here in the expansion. That's why we adjusted 1 by n factorial into this. That means it will be t to the power n into this quantity that will be formatted as h and z. So we are taking this result. So we find the generating function for Hermite polynomial. This is a very useful functions, and with this help of functions we can generate and we can solve many type of recurrence relations. We can easily get in this way. Now let's see how these things happen. Let us consider the first recurrence relation. Prove that h dash nz, that will be 2n hn minus 1z for n greater than equals to 1, because it is our definition criteria, otherwise it is not defined. Now we have e to the power minus t square plus 2tz is equal to this quantity sum of n is equal to 0 to up to infinity t to the power n by n factorial h and z. Now differentiating both sides, we get differentiating both sides with respect to z, we get if we take differentiation with respect to z, that means here it will be two t into e to the power minus t square plus 2tz, and with respect to z, that means sum of n equals to 0 to up to infinity tn by n factorial h, this derivative dash, which imply 2t into, if this quantity is sum of n equals to 0 to up to infinity tn by n factorial h and z, and n equals to 0 to up to infinity t to the power n by n factorial h n dash z, which imply 2 into sum of 0 to up to infinity. Here if any t is included, then t to the power n plus 1 by n factorial h and z, that will be sum of 0 to infinity up to t to the power n by n factorial into h n dash z. If we reply this and replace n by n minus 1, then sum of n equals to n minus 1, that is n equals to 1 to up to infinity t to the power n by n minus 1 factorial. Here it will be n minus 1z to adjust, and here it will be n equals to 0 to up to infinity t to the power n by n factorial into h n dash z. Now equating the coefficient of t to the power n, we obtain, just to take the coefficient, 2 by n minus 1 factorial h n minus 1z is equal to h dash n z by n factorial. and which imply if we replace it 2 into n factorial mean n minus 1 factorial by n minus 1 factorial hn minus 1 z, that will be equals to h dash z. Therefore, h dash z equals to 2n n minus 1 factorial by n minus 1 factorial into h n minus 1 z. We rewrite this equation once more, which imply h dash n z. These two terms will cancel, 2n into h n minus 1 z. Then finally we prove this result. Therefore, we finally rewrite h n z equals to 2n h n minus 1 z for n greater than equals to 1. Now we end our discussion today, just to give the idea of Hermite polynomial and as well as apply it to establish one recurrence relation for Hermite polynomial. We end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks.